Okay. Hello again. For the purpose of recording, hi, I'm David. I'm the coordinator of the Maths Learning Centre at the University of Adelaide. It's semester 1, 2021. And here we are, both in the Flenchy Lecture Theatre and on Zoom, doing a revision seminar for Maths 1A. And everyone has decided that we should first talk about subspaces and basis. Okay. The rules are, for this seminar, that it belongs to you. So if you think of something that you would like me to talk about, then allow me to finish a sentence, but then feel free to interrupt. If I think that I'm going to talk about that anyway, I might get back to it later, but it's your seminar, and that goes for you online as well. Every 5 or 10 minutes, I'm just going to stop and ask if people have questions, so you don't have to interrupt me if you don't feel like it. And all questions are worthy questions. And it's your seminar. So I cannot be offended by asking questions. I can't be offended if you leave. I know everyone has places to be, so feel free to just go if you need to. Don't make a big ruckus as you do, but I'm happy for you to go. And yeah, all questions are good questions. Okay, just letting you know. So, I'm just going to make sure that that's as clear as I can make it. Good. The irony is that I can't get Zoom to work on the lecture theatre computer, but I can't get. Yeah. Anyway, it's just awful. So here we are talking about subspace and basis, and this is one of the big ideas in Maths 1A and in Maths 1B as well. You do more of it in Maths 1B. Just warning, if you do that course, that it will come. So if you get it done now, then you'll be well prepared. But even when you get to Maths 1B, happy to talk to anyone about it. It can be a tricky thing to get a handle on. Right. Let me just think about where I'm going to start. The first thing I'm going to say is what vectors are. Bear with me, and I will get to subspaces soon, but I just want to talk about a few things. To a physicist, a vector is a quantity that has both magnitude and direction. To a mathematician, a vector is a thing with coordinates. That's pretty much it. In fact, that's not quite right. To a mathematician, a vector is a collection of things are vectors if you can add them and do scalar multiplication on them. That's what a mathematician thinks a vector is. So there's two things that a mathematician thinks a vector is. Things are vectors when, I'm going to go in a bit. You can do plus and scalar multiplication, or they have coordinates. And that's pretty much it for a mathematician. The philosophy of what a force really is irrelevant to us as mathematicians. Physicists can think about all of that stuff. That's what we're interested in. So importantly, nothing is a vector all by itself. They're only vectors because all of them together are vectors. They do scalar multiplication and addition. And they have coordinates too. And so we're used to things like this, e.g. things that have real numbers in these spaces here. This thing is a vector in R3. The 3 is referring to how many coordinates it has. The R is referring to the real numbers that can be in these spots. It is possible to be in something like Z3, where the coordinates are only allowed to be whole numbers, for example. But we're interested in R3 in this course, or R2, or R7, or R anything. And so to a mathematician, something with 7 coordinates is not a problem. It just has 7 coordinates. And that's all there is to it. Just a list of 7 numbers. Yay! You don't have to worry about trying to imagine what 7 dimensions look like. It's just numbers. Luckily, we can know what R3 looks like because we live in R3, and we can borrow what we know about how geometry works in R3 and reuse that in R7 if we need to. And that's why you're learning about this, because most of the times the vectors you're really interested in don't have 3 coordinates. Because a vector represents any list of numbers, and most situations have more than 3 numbers to describe them. A bicycle all by itself has at least 7 numbers, because, you know, this is a very bad bicycle. There we go. And it's, you know, it's this wide this way, and it's this wide this way, and it's this high. That's 3 numbers. And then this wheel can be like that far round, and this wheel can be like that far round, and the handlebars can be like that far round. That's 6 numbers already, and I could use those numbers to describe my bicycle. And now my bicycle is a 6-dimensional object, 6 numbers to describe it. But I could also stick the temperature, you know, if I wanted, that's a 7th number, all sorts of things. And that's a really stupid example, but if you were building, say, a robot arm that was supposed to pick things up, each piece would have a certain orientation, which would be at least 3 numbers to say which orientation each piece of the arm is in, and all of those numbers are related to each other. Okay, cool. Right, that's what vectors are. The important thing about vectors is this. You can do addition and scalar multiplication in the way that you want to. You know, you can keep multiplying by scalars over and over and over, and it'll have the same effect as those numbers combined. You can add them in whatever order you want and get the same answer, those sorts of things. And mathematicians have a nice list of all those properties, and they call a set of vectors that does those things a vector space. So the set of all the vectors of the particular type you're thinking of are together a vector space. I mention this because that word space is the piece of the word of subspace. I need to say it so that the word subspace makes logical sense in terms of language. Okay, cool. One more thing to say about vectors. If you're going to think about them as geometry, then a vector is a point. Yep, that's pretty much it. It can be an arrow if you're thinking about adding it to stuff. So if you're thinking about doing these operations, then you can think of it as an arrow. But if the vector's there all by itself without anything being done to it at the moment, then it's a point. They're points if they're just there. And arrows if we're adding them, or scalar multiplying, so doing things. This is the technical terminology stuff. It's not really, I'm just making crap up. Okay, but it's really important to know that when mathematicians talk about vectors being in places, they're talking about just the point that these 3 coordinates or 7 coordinates or whatever describe. We're not thinking about the whole arrow that goes from the origin to that spot as being in a place, just the dot at the end. That's the thing that we're thinking of when we talk about a vector being in a certain place. Okay, that's vectors. The next thing I need to talk about is sets. A set is a collection of things that has a rule for deciding whether you're in it or not. There has to be some sort of rule for helping you decide whether something is in the set or not. And that rule has to be unambiguous and easy, not easy, but has to not be able to have any contradictions when you attempt to think about it. You know, okay. So in this area, sets come in two main flavors, based on the way that you decide whether things are in or out. So one example, this set, the set of things x, y, I should probably be more specific, in R2, damn it, where's my good eraser? So this is the set of things x, y, which are in R2, which tells me that this x and this y are real numbers, such that x minus 3y is equal to 7. Some people will write a colon in that spot there instead of a vertical bar. There's just no consistency there, it's just the way it's done. Okay, so you'll notice that this tells me the kind of object I'm thinking of. I'm thinking of vectors in R2, and this tells me a rule they have to satisfy. And I can tell whether a vector is in that set by subbing it into the equation and seeing if it comes out to 7. I should give this set a name. I shall call it S. So the point 1, 2, if I go 1 minus 3 times 2, I get -5, which is not 7, and so this is not in the set S. So this symbol means in, and means, you know, is in, and crossed out means is not in. Okay, whereas, oh gosh, 28, 7 is in S because 28 minus 3 times 7 is indeed 7, and so this one is in S. And that's basically it. You could think of vectors as long as you wanted, and any vector you thought of, you could decide if it was in the set by putting it into the equation and see if it works. And you can have anything you want in this spot, as long as it's a rule that you can attempt to satisfy. So it could be 2 equations and you have to satisfy both of them simultaneously. It could be just information. It could say, oh, well, you know, they all have to be integers. Anything like that, which is a rule that you can look at and go, yep, I can tell. And it's almost always an equation. But it doesn't have to be an equation. It can be a less than, you know, the x coordinate has to be less than 5, in which case this one would be in it and this one wouldn't. Any of those things are okay for making sets. As long as there's a rule to decide, it's a set. And when we think about sets, we think about the rule, but then we also try and think about what would happen if we colored in all the points that were part of the set. And in this case, this would make a line when I colored in all of those points. I've made a very terrible equation. So when y is 0, x is 7. When x is 0, y is minus 7/3, which is 2 and a bit, about there. So any of these points, if I put them into the equation, it doesn't work. None of these work, and all of the points on the line work. So together, this set is this drawing. Yep.
So that graph you draw, is that a vector space?
No, this is the vector space,
Yeah.
and that is a set. That's it. I mean, it's a line, obviously, but yeah. In terms of vector space terminology, it doesn't have a name of its own. It's just called a set. Some sets are special. We're getting to that. So this is one kind of way to make a set, to have a rule to decide whether it's in the set or not. There is a separate way to make a set, which is this. So an example, I shall call it T because that's the next available letter. This one has the rule first. No, not that one, sorry. So when you read this aloud, this is the set of things which have as their first coordinate 7 plus 3t and their second coordinate t, such that t is a real number. So this is giving you how to make the thing. And this is some technical details. Just to make sure that I'm supposed to use all the numbers that are real numbers, and I'm supposed to create all of these things, and then all of those things, they are the set. This one tells you a rule for deciding whether a random thing is in the set. This one tells you how to create all the things that are in the set. So I would make, to use this, I would say, oh, well, you know, when t is 0, I get 7, 0. When t is 1, I get 10, 3. And when t is a half, I get 7 plus 1.5, which would be whatever that is, 8.5. I shall just write it as 8.5 and a half. And when t is root 3, I'll get whatever 7 plus 3 root 3 is. And I can make as many of these as I want. What it's difficult is to, if you have a random point, deciding whether it's part of this set or not is tricky. Because, you know. So this is definitely in t, and this is definitely in t, and this is definitely in t, and this is definitely in t, because I made them the way that it says to make points in t. If I ask myself, you know, is the point 15, 5 in t? Then the only way to tell would be to see if it's possible to make it in this way. It would have to be equal to this. And that would mean the t would have to be 5. And that would mean the 7 plus 3t would have to be 7 plus 3 times 5, which is 7 plus 15, which is 21, which is not 15 like I said it was. Yes? Totally would be 10 and 1. Good job. Excellent. So 10 and 3 wouldn't be in this set, because if it was 3, this one would have to be 16. Right, gotcha. So this is not the point that I've got. The only way to make a point in this set that has 5 as its second coordinate is for the first coordinate to be 21, and it's not. And so this point is not in T. Okay, so no pun intended, the point I want to make here is that this sort of set here and this sort of set here have two separate purposes. This one is for deciding whether things are in the set. That's really easy with this sort of thing, but it's difficult to just come up with points that are in this set. That's quite tricky. If I said to you, come up with a point that satisfies the equation x minus 3y equals 7, you're going, oh, the y could be 0 and then the x would be 7. Great. But you'd have to think about it. Whereas this one, you can come up with points that are in this set, as many as you want. Just keep picking values of t. But it's difficult to tell if things are in this set or not. And this tension between these two things is one of the big issues of linear algebra. Okay. I think at this point, it would be useful for someone to say something, a comment or a question of some sort. Thank you. I'll take the one that we said earlier, the questions that were there as what I said. And someone said there are two types of sets. These are the two types of sets. They're really just sets. It's just I've described them in different ways.
Is there a way to write one set in both ways?
Is there a way to write one set in both ways is the question I've been asked. And the answer is yes, good question. Because these are actually the same set. This set is the same set as this set. So if you've studied certain terminologies, someone will call this a Cartesian description of this set, and some people will call this a parametric description of this set. One of the ideas that you use in subspaces is converting between them. And you actually know one of those ways, and it will be clear soon. But if I attempt to draw this, then the quickest way would be 7 plus 3t would be 7, 0 plus 3t, because they're vectors, I'm allowed to split them up with addition. And this would be 7, 0 plus t lots of 3, 1. So this is saying that it has the point 7, 0 in it. And to get to all the other points, I keep having to add on multiples of this vector. And so this would be 1, 2, 3, 4, 5, 6, 7. And I could add the vector 3, 1 from there, which would be there. I could add half of 3, 1, which would be there. I could do minus 1 of 3, 1, which would be there. And I could fill out all the possible choices. No, 2 lots of 3, 1 would put me there. Adding minus 5 lots of 3, 1 would be here. And that would produce all of these, which is the same as this. Yay. Good-o. So in this course for subspaces, you have mainly learned, and I will show you how, to get from here to here. Some of the tutorial and assignment questions have covered how to get from here to here, but it's not like a procedure they want you to be able to do quickly. But it's still something that's worth knowing about. Okay. I will do one final. There's really 3 kinds of sets. And the other one is just to list all the things in the set. 1, 5, and 2, 1/3, and 5, 0. That is a set that has exactly 3 things in it. That dot, and that dot, and that dot. That's all it is. It's just 3 dots. It's just a list. These are the 3 kinds of set. The only other thing you can do to make sets is once you've got them, you can glue them together and you can intersect them and you can do all those sorts of operations on sets, but this is what I'm going to talk about right now. Okay, there are things you can say about sets. You can say a set is convex or not convex, which is a whole separate part of this course, which if you want to talk more about, you come to Maths Learning Centre. And there is a very special kind of set of vectors, which is called a subspace. Right. But before I do that, I want to talk about one more thing. You have to have all this or it's not going to make any sense. And I want this to be able to be watched by someone at the beginning of next semester's Maths 1A to try and make the stuff that comes later sensible. Okay. Good-o. So the next thing is linear combinations. Right, let's just see where we've been. Vectors are things that have coordinates, and they're points or possibly arrows if you want to start adding them and multiplying them. And they make sets. And a set has a rule for deciding if you're in or out. The big question is if you just have a random drawing, how do you figure out what set it is? But we'll deal with that later. This idea here, this first thing that I said, doing plus and scalar multiplication, there's a word for doing both of those at once, and it's called a linear combination. So if I have some vectors, and I do this operation, some number times this vector plus some number times this vector, that thing is called a linear combination of those vectors. I am deliberately not using letters in this spot because I don't want it to get bogged down in notation. If you ever have some number times one vector and some number times one vector and some number times another vector, that's called doing a linear combination. And the answer is a linear combination. It's a fancy word for just the thing that vectors are designed to do. The only reason we're allowed to call them vectors is because they do addition and scalar multiplication. That's what vectors are, things that do that. And so a linear combination is a combination of both of those things, addition and scalar multiplication. And this is the heart of pretty much everything in this course. That's what vectors are for, doing linear combinations. This here is a linear combination. It's 1 of this vector and t of this vector. Already made one. That's pretty much it. Like, just know that that's what happens. But it's really important to know about this because every time you do matrix multiplication, you are doing linear combinations. So if I had a matrix that had certain columns and I multiplied it by a vector, this has 4 columns, this has 4 things. That's how matrix multiplication works. I could think of it as row times column and row times column, but I can also think of it as that when I do this matrix multiplication, everything in this column is going to get multiplied by that number. And everything in this column is going to get multiplied by that number. And everything in this column gets multiplied by that number. And everything in this column gets multiplied by that number, if you do the whole thing. And so I'm going to get number times first column plus number times second column plus number times third column plus number times fourth column. Matrix multiplication is performing a linear combination. And that's why matrices are so damned useful for thinking about vectors. Okay, so I'm just going to write that down. Matrix times column vector equals linear combination of vectors. That's one of the things it is. Matrix multiplication is really flexible and it means lots of things. In fact, if I did a row times a matrix, that would be a linear combination of the rows. So, yeah. Okay. One more thing about linear combination before I move on, and it is this. Span. The word span is one of the major, well, and the things connected to it is one of the major confusions in this course. If you are confused by this, that is usual. You are, I'm sorry to say, ordinary if you are confused by span. Sorry, you're spectacularly stupid, but you're not. It's just ordinary. Span is, the worst part of it is that span is so much less than it seems. So, you know how we make linear combinations? If you thought of some vectors, you know, 1, 5, 0, and just some random vectors, 2 random vectors, and I think, well, I can do linear combinations. I could do this one, I could do 1 of this one, and 2 of this one, and that would produce 1 plus 4, which would be 5, 5 plus 2, which would be 7, 0 minus, so that would be that there. And I could do like 100 of this one, and you know, 10 of this one, because that one's easy for me to do. So I'll get 120, 510, and minus 10. And I could do none of this one, and minus 6 of this one. Oops, sorry, I better not change the actual vector. That would be confusing. So I have minus 12, minus 6, 6. And I could do like half of this one. And I could do this as long as I wanted, right? Because, you know, whatever. These are all linear combinations of the original 2 vectors. That vector is a linear combination of those 2. That's a linear combination of those 2. That's a linear combination of those 2. If I imagine all the possible answers that could possibly happen if I did linear combinations, all of those things together, That's the span. That's what span means. The action of spanning is making all the linear combinations. Right. So if you've been paying very, very close attention, you would have noticed that I use the word span in two ways. Here it's a verb. It's an action that performs things. And here it's the name of the thing that I produced. It would be a little like the word caking, meaning to make a cake. Spanning produces a span. Okay. Now, I have one thing to say about this, but before I say that, I would like anyone to ask a question. Yeah.
Incorrect if the two vectors you use to define span as the bounds of all the vectors that you deposit.
I'm just going to repeat that to make sure I understand so that these people hear it too. Would it be correct to call them these two vectors here like the bounds?
Yeah.
I get what you're saying, but the word bound already has a meaning in maths because they don't sort of tell you the edges.
But they kind of define the area.
Yeah. I would like to talk more about that. That's a good question that I want to build on. In the comments, I'm just going to read it. How can we find the span? I'll get onto that. When it is said that the set of vectors span a subspace V, does that mean the span of the set of vectors is V or the other way around? Okay. And I'll read the other question too and decide which order to do them in. If you had a set of vectors in R3, you had 3 points, would that form a span plus a basis of a plane right? If you had another point, no longer form a basis. Right. That's a very, I will answer that when relevant, Joshua. There's a lot in there. So, okay. I will get back, Pandula, I'll get back to your question as well, and I'll talk about yours too. I'm just going to talk a little about what happens when you span visually. So this vector 1, 5, 0 and 2, 1, minus 1, I'm just going to change them because I don't want to do negative ones because my diagram is not going to work if I do. And I'm going to change it to be in R2. Let me just do the span of one vector first. Here we are in R2. I know I'm in R2 because there's only 2 coordinates. And here is the point 1, 2. And I would like to imagine the span of 1, 2, which means I need to think of all the combinations that are something times 1, 2. Because there's no second vector to add to it, so it's just all the multiples. So 0 times 1, 2 would be there. If I think of it as an arrow, 2 times 1, 2 would be twice as far, which would be there. Half of 1, 2 would be there. Minus 1 of 1, 2 would be the opposite direction. Minus 3 of 1, 2 would be there. And I could put in a third of 1, 2 and 1 1/2, minus 1 1/2 of 1, 2, and I could fill out all of this. So this vector 1, 2 produced the line. So it's not really a bound in the sense of defining the edges. It sort of defines the inside. I started in the middle here and then went outwards from there. So that's why I find it difficult to call it a bound, because in maths a bound is the outside. And that is why we use the word basis in maths. We need a new word for what this is. We call it a basis. It's the inside of the thing, the starting place that I use to build the rest. That's what the word basis is about. We have to adjust our meaning of basis a little later when we've learned some more stuff, but that's what a basis is designed to do. If you've got a thing, a subspace, it has to be a subspace, and we'll get back to what that is in a minute. If you've got a thing and you would like to rewrite it as the span of stuff, then the stuff is the basis. Okay, let me just step back a bit. You said, when we were back here and we were looking at this, how do I rewrite this in this other format? Well, span is that other format. I'll get back to that. Thinking about too many things at once here. So if I'm going to span two things, I'm going to be in 3D now. Well, I'm going to say I'm in 3D, but I'm not going to be. So in 3D, I could have an x-axis and a y-axis and a z-axis pointing upwards from my page. But luckily, these 2 points have 0 as their z-coordinate, and so they're going to be on my piece of paper. So it's technically in 3D, but it will fit on my page. So that made me happy. So we have 1, 2, which is here. 1, 2, and 0 that don't go up in the z. And 3 minus 1, 0. So that's that point there. And I can imagine that there's arrows here because I'm just about to do addition and scalar multiplication. So the span would be all the things that are made of the addition of these two things or the multiplication of those two things. If I do all the scalar multiples of this one, I'm going to get this line. And if I do all the scalar multiples of this one, I'm going to get this line. And now if I add one of these vectors to these vectors, this plus that would be there, this plus 2 of that would be there, this plus 3 of that would be there, this minus 1 of that would be there, I'd be able to fill out this. I could have half of this plus 1 of that, that would be this. I could have 2 of this plus all the multiples of the other, that would be this, and I'd fill out everything. But it's not actually everything, because this was just a plane inside 3D. There's a z-axis here too. So what these two things did is they produced a plane together. That would have happened even if they weren't sitting flat on the page. If I had had something that was more like, there's my z-axis, and I could have had that vector and that vector, that vector. I'm running out of space, I'm going to put my z-axis down. Then this one plus that one would give me here in space. Half of this one plus a third of that one would be about here, and those two would together make a plane that sits neatly on top of them, angled in space. If you ever want to do this live, come to the Maths Learning Centre and say, David, could you show me vectors on the floor graph? And we can walk it out. Okay. Okay. So what span means is that any two vectors will together form a plane. One vector by itself will create a line, and they'll fill in all the spaces. And whenever you make a span, you always make the 0 vector because you can always have 0 of this one and 0 of this one. And so this action of spanning always produces a subspace. Actually, it does. It always produces a set that passes through the origin, and it always produces a set that's sort of flat. It's either a straight line or a flat plane. And we need a name for that kind of thing, and it's called a subspace. Whenever you span anything, you always produce a subspace. Okay. Right. And so someone in the chat has just asked a very important question, and this spans R2, and the answer is no. And that's to do with a very special use of the language in maths. R2 is made of things that have 2 coordinates. These vectors have 3 coordinates. They're never going to be in R2. R2 is only made of things with 2 coordinates. The previous example. This one does not span R2 either. But I haven't got to one last piece of language about how span is used. So these are very important questions. So we've said what a span is. And someone asked, how do you use the terminology of span when you're talking about it spanning a thing? So when you say, you know, the vectors, whatever they are, span a thing called V, what that means is when you do the action of spanning, then what you produce is V. So this is short for the action of spanning these things produces the whole of V. This is what I say in my head. This is the maths terminology. And the mega maths terminology would be V is the span of those 2 vectors. So over here, this line is the span of 1, 2. R2 is the whole plane. This span does not cover the whole plane. So this vector does not span all of R2 because it only covers this bit. This point here, for example, is not in this span, and so the whole of R2 is not part of this span. So I would say that 1, 2 does not span R2. But what it does span is a line, this line. Yeah.
So with that, would it be that we need at least 2 coordinates or 2 like vectors to be able to actually span R2?
Yes, you definitely need 2 vectors to span R2. You can do it with 3, you just don't need 3. Okay. And what you've described there is the idea of dimension. And we'll get back to that. Okay, so, right. So there's lots of questions going on, and they're excellent questions. I'm going to go back to here, this set here. This set is not the span of anything. I said this is a linear combination, but a span is all the linear combinations. And to make this set, I'm only allowed to have one of these vectors 7, 0. I can have as many of the 3 1s as I want, but I have to have exactly one of the 7, 0, or I won't make this line. So this line is not the span of anything. I cannot make this line as a span. So when Joshua asked, does a spanning set have to cross the 0 point to be a subspace? A spanning set is guaranteed to cross the zeros, to cross 0. But another set that doesn't cross 0, it's impossible for it to be a span, and so it's not a subspace. I think I'm nearly ready to talk about what a subspace is, but I think we need to clarify what's happened just here. So, we had vectors which were points. And when we were thinking them, and we were allowed to, with these points, add them and do scalar multiples. And if I get 2 of them or any number of them, and I do all the scalar multiples and all the addition, it will create a set. And that set is called the span of these vectors. So if this is the vector v and this is the vector w, then all of this would be the span of v and w. Oh, crap. Okay. And I said that a span is a subspace. And I haven't talked about why it's called sub and why it's called space. And I will talk about that now, unless someone has anything else to clarify that I've said already. Yeah?
You know how you said if
3 vectors. Should have brought my Play-Doh. 3 vectors.
Yeah.
So these two together, they'll make a plane.
Yeah.
And then after I've already made them, I can also add this one as well. So these 2 vectors, and then I can add as many of this as I want, and so I'll be able to fill out all the rest of space. I'll make a 3D space. If I was in 4-dimensional space where there was even more room, then there would be even more stuff that I could make by adding a 4th vector, which is difficult to imagine. But yeah, 3 vectors would make a 3-dimensional space, except if the 3rd vector I picked was already a combination of these 2, I wouldn't make any more. So I could do like 1 of this one and 2 of this one, which put me there, and then 3 of that one, which would be there, and it would still be in the plane, and I could have made it out of just these 2 if I wanted. And if I had 2 vectors, then sometimes if they're already pointing in the same direction and I span them, I still only make a line because one of them is already a multiple of the other one. Yep.
Does the number of coordinates affect what's created as well? Because like with like 3 vectors, vector with 3 coordinates you get a plane, and 2 coordinates you get a line.
So the number of coordinate, good thing. And in fact, that relates to my t-shirt, which says beware of the toast, which means be careful of basing your decisions on a list of examples. And you can read the back one day and find out more about that. Right. This one, when there were 2 coordinates, made a line, and this one, where there were 3 coordinates, that made a plane. It's not the number of coordinates, it's the number of vectors. So if I was in 3D and I had the span of just 1, 2, 0, it would also be a line. Because here's 1, 2, 0, and there's 2 of 1, 2, 0, and there's half of 1, 2, 0, and there's 0 of 1, 2, 0, and there's minus 1 of, it still makes a line. So it's the fact that it's one vector that causes it to make a line. It doesn't matter how many coordinates it has. It's just this one is a line that's part of 3D space. And this one's a line that's part of 2D plane because of how many coordinates there is. So the coordinates tells you how much space there is to fit your line in, but it doesn't tell you how big it is. You have no idea. But what you do know is that if you have 3 coordinates, if you have 2 coordinates, you can't make anything more than a plane, because a plane is everything when there's only 2 coordinates, so you can't make anything more than that. So that's what it does tell you. Does that answer the question? Okay. Right. Okay. Cool. So we're nearly there. Way back at the beginning, I said that there was these 2 kinds of set. A span is the second kind of set. Because when I say the span of, 1, 3, 5, and 0, 7, minus 6, that's short for saying the set of all the linear combinations of these things. So this is what a linear combination looks like. And I have to have all the possible numbers. So this is an alternative way of writing this, because this is a linear combination and you have to use all the numbers. But this is also one of these. How to make the object, that's this bit, this is how to make it, and some technical details of what the letters mean. So this is that second kind of set. It's a set that tells you how to make every point in the set. There you go. Okay. We're now at Subspace. We're finally there. How long have I been going? About an hour. Okay. Right. It deserves a whole new page of its own. The problem with this sort of thing that I'm doing is that it doesn't write down on paper very well. And so my notes are yeah, they're just not going to be productive. But it's the sort of thing that if you're talking with someone, you can imagine the pictures. It's a little easier to process. Okay, so now we're at subspace. So you need to imagine now that I didn't say that to make a subspace you do a span. It's true, but now you imagine that you walked in now at this point and you hadn't heard me say that, and you were thinking about the idea of a vector space. So a vector space is made of things which I choose to call vectors that do addition and scalar multiplication. Which means they're things that do linear combinations, right? Because linear combinations is both of those at the same time. Okay. What if I wanted to make my own vector space out of other things? I can do that actually. As long as I can find anything that makes sense to do plus and scalar multiplication, it's probably, I could call them vectors if I wanted. So in differential equations 2, which you may do, there's one called for engineers and there's one called for maths. In differential equations 2, you start going, functions, I can add them and I can multiply them by scalars. I'm going to call them vectors. Matrices, I can add them together and multiply them by scalars. I'm going to call them vectors. And the reason you would do that is you'd borrow all this stuff you know about vectors and know new things about functions and matrices. Okay, but we're not going to do that today. What we're going to do is saying, just a second, what if I didn't use all the vectors in R3 and just had some of them? Could I chop away all the rest of R3 and just have this plane? And could they act like vectors all by themselves without interacting with the rest? Could I have a smaller piece of it? This is my little vector space that's a vector space all by itself. I don't need the rest because I only care about what's in this plane. And the answer is yes. That's what a subspace is. Okay, it's completely self-contained when you think about linear combinations. So the reason it's a space is because we're referring to vector space, and the concept of space is three-dimensional space. And it's a subspace because it's inside another space. Sub is Latin for below, or after, or inside. It's like anything that's sort of subsequent, that's what the word sub in subsequent means. Anything that's subsequent to another thing, that's what sub means. And in mathematics, if you say sub thing, it means one of these things, but it's inside another one. And that's why we talk about a subset. We've got a set, and we've got another set inside the set. That's a subset. We've got a space. We've got another space, a space inside the space. That's a subspace. We've got a city, which would be an urb, because urban means city. And you've got another city inside the city. That would be a suburb. That's how it works. Okay? So that's the idea. And it has to be, the idea is it's not just a thing that's inside the subspace, it has to count as a vector space all by itself. So if you just look at just that bit, it has to work like a vector space, which means all the linear combinations have to be there. It has to be completely self-contained. So this is the idea. So the thing that vectors do to be a vector space is linear combinations. So if I want a smaller piece of it that counts as a vector space all by itself, it has to be self-contained when I do linear combinations. It has to be impossible to get out. So here's my other thing. It's inescapable. You can't escape a subspace by doing linear combinations. So here I am, my table. is a plane. It's in R3 because, you know, there's R3, right? And it's not all of R3, it's just a piece of R3. And if that table here, let's say that's the zero vector there, then, you know, if I add this vector to this vector, I'm still on the table. If I have 5 of this vector, I'm still on the table. And no matter which ones I make, if I still do that, I'm still on the table. I mean, this table technically is not self-contained because it ends. And I could do 5 of this, 20 of this vector and I'd fall off the edge. It's not self-contained. So if I want it to be a subspace, my table's going to have to go on forever. And this piece of paper could be a subspace if it contained a zero vector. And if it went on forever, of course. But if I did this, that would not be a subspace, because if I took my vector and multiplied it by 3, I would fall through the hole. Subspaces don't have gaps in them because you can escape them by multiplying by stuff, or adding stuff, or subtracting stuff. That's the idea of a subspace. It's completely self-contained. It has no gaps, no holes. It goes on forever. No gaps at the edges, no gaps in the middle. It goes on forever. No matter what combination you do, it's completely self-contained. All right. How do people feel about that? Right. So what I've done, it has to contain the zero vector, yes, because one of the combinations is 0 of this and 0 of this. So if there's a hole at the zero vector, it's going to fall out the hole. Okay. You need, whenever you learn a new kind of object, you need a list of things that are and a list of things that aren't, because that's how human brains work. When you learned what a dog was, you saw several dogs and went, that's what a dog is. That's pretty much it. And you saw things that weren't dogs, and you went, well, they're not dogs. And you asked your parents, is that a dog? And they went, no, that's a koala. Or whatever. And it can be a bit confusing because in real life, most of these things don't have good definitions to tell where one thing ends and the next begins. It's like, that's a wolf. Is that a dog? Yeah, no. But in maths, we have definitions that say where the end of something is and where the beginning of the other thing is. So that's why we need this thing. So we have a definition for a subspace, and that's the line, but I'm still going to give you a list of things that are and a list of things that aren't. So you can tell just by looking at it whether you think it's a subspace or not. Because there's a classic question that you could ask yourself that tends to turn up in exams and Mobiuses that says, here's a list of things, which ones of them are subspaces? You shouldn't have to use the definition for everything. You don't have to, the biologist has a definition of what a dog is. You don't sit there and go, it's got fur, it's got a tail, gives milk to its young. Like, you don't go through the list. You just look at it and go, it's a dog. I know what a dog looks like. That's what I want for you for subspaces. But we do need a definition. So the definition is a set in R or whatever is a subspace when, I should give the set a name, I shall call it S. I believe it's traditional to call it W, but it's in there now. The zero vector is in the set. That's the first thing. Technically, you don't need to check that the zero vector's in, you just need to check that it has at least one vector, and then the zero vector will be in there for free. So if you ever do another course later called Algebra 2, they might have a slightly different definition, but it all works out fine. And note that if you look at stuff online that's from the USA or Germany or whatever, they might have a slightly different definition with respect to this one. They might not say that the zero vector's in it, they'll just say it's not empty. Like it has at least one vector in it. Okay, and if two vectors are in the set, then when you add them, it's in the set. And if one vector is in the set and another, and k is a real number, then k times this is in the set. So these two together is telling me that it's self-contained with respect to linear combinations. If I do the addition and if I do the scalar multiplication, I only produce more things that are in the set, stuff I already had. Okay, that's the definition. If you're ever asked to prove that something is a subspace, you have to use the definition. Pardon me. If you're ever asked to just say, is it a subspace, give me a reason, then you can say, well, you told me that these things are subspaces. I don't have to check the definition. It's already done. So here we go. Pictures. Subspaces are lines and planes and flat things. They don't have holes. Lines and planes and 3D spaces and whatever. They don't have holes and they go forever. There's only one subspace that doesn't go forever, and it's the one that's just the origin. Because you can't escape the zero vector by doing multiplication, because every time you multiply it by something, you've still got the zero vector. And you can't escape it by adding, because every time you add it to itself, you've just got it again. So it's impossible to escape the zero vector by doing those operations. It counts as a subspace all by itself. So, you know, a single point, right? But importantly, they have to go through the origin. So things that satisfy all these things, they are subspaces. So if someone said, you know, is this thing a subspace? And you go, well, it's a line, it doesn't pass through the origin. No, it's not a subspace. That's it. It's the wrong shape. Well, I mean, it's the right shape, it's in the wrong place. In fact, a line that's not through the origin is the worst kind of not subspace, because it breaks all of the rules all the time. Let me show you. Here's a line that's not through the origin. It doesn't contain the origin, breaks rule number 0. I normally call this rule 0 and rule 1 and rule 2. Because this one has the zero vector, this one involves, oh crap, I normally write them in the opposite order too. Like, this is rule number 1 because it only has one vector, and this is rule number 2 because it has 2 vectors. So I normally, if I was paying attention, I would have written them in the opposite order, because this one's easier to check than this one because it only has one vector. So, all right, so here we are. Rule number 0, broken. Zero vector is not part of the line. That's enough to tell you it's not a subspace, but let's just go overkill. If I have any point in this set and I think of it as a vector and multiply it by something, then I will fall off the set, no matter where I am. This one fell off the set. This one fell off the set. This one multiplied by half this time fell off the set. If I have any vector and I multiply it by anything other than 1, I will not be in the set anymore. It breaks the scalar multiplication rule for every possible point. And if I have 2 vectors and I add them, it will fall off the set. A line not through the origin breaks all of the rules all of the time. So there was a classic Mobius question that says, here is a set, pick 2 vectors that breaks the addition rule. If you notice that it's a line, any 2 vectors will do, they'll all break the addition rule. It's one of my favorite Mobius questions. Yeah, because I like those sorts of things. Yeah, so there you go. Okay, so anything that's curved won't be a subspace, because that curve will cause there to be a gap. So this parabola, it does pass through the origin, but look, this point, if I multiply it by 2, not in the set. So anything that's curved won't be a subspace because it'll break the scalar multiplication rule. So here's a question, and this is a sort of thing you should do when you learn a new thing. What if I would like someone to see if they can think of a set which satisfies the scalar multiplication rule, but doesn't satisfy the addition rule. It's tricky. You can do it. Yep.
Like a line that doesn't go forever.
Okay, so I have to satisfy the scalar rule. So you're telling me if it doesn't go forever, that's going to break the scalar rule. Because if I pick a point on it and have a big enough number, it'll fall off the end. So what Tom has told me is that this tells me that if it's going to have any points in it at all, and it satisfies the scalar multiplication rule, it's going to have the entire infinite line. Yep. So you're telling me this satisfies the scalar multiplication rule? It does. I'm just asking you if that's what you were saying. It does. No matter which one I pick, if I multiply it by any number, then I'll still be inside the thing that I coloured in. I'll never be able to get from here to here, but that's not important. The point is I just want to still be inside it. But it will break the addition rule, because if I pick this one and add them together, then I fall off the set. So well done. This is anything that's like a star that goes through, that's made of lines through the origin, will satisfy the scalar multiplication rule. But if there's any gaps between those lines, it'll be won't satisfy the addition rule. It's really difficult to satisfy the addition rule and not the scalar multiplication rule, but it is possible. I would draw all of the grid points. Like only the ones that have whole numbers forever, and so on. Can't be bothered drawing all of them. Just a second. Right. See, now you can pretend it goes on forever because you can't see the rest. If I add any two of these together, it'll get one of the other ones. So like this one plus this one would be there. And so if you add them together, you'll get any of the others. So it's closed under addition, but if I multiply any of them by like a half, I'll fall off the set. So it's fun. I love doing this sort of thing. Won't happen in the exam probably. That's a bit too vague a question to ask. But I would love it if it did, because you'd all get it right, you know. They'd say, give an example of a set that's closed under scalar multiplication but not addition. This set. Yes! If you would like to know how to write this set down, this is the set of points x, y, such that y equals x, or y equals minus x. You just have to use the word or. It's a perfectly good condition. Whereas this one is the set x, y, such that x and y are both in z. X, y, such that y is equal to x, or y is equal to minus x. Okay. Right. So points and lines and planes and 3D spaces through the origin, definitely subspaces. They are the only kinds of subspaces. All subspaces look like that. So if it is not that, it must be something else. It's just a generic set. It's not a subspace. If they have holes, if they don't go on forever, definitely not a subspace. So this would be requiring you to have a good idea of what things look like. If you're allowed to use Desmos,
Yes.
which those listening in the future, this may not be true. But for semester 21, 2021, it is true. Then you can put an equation in and it'll tell you what it looks like. Well, we may go back to face-to-face exams in an exam hall, so yeah. Okay, so that's what it looks like. But I want to show you something that I did. Usually if someone says, is it a subspace, and you say no, usually you need to give an example of some points that break the rule. And so if someone said, is this a subspace? I would say, in my head, I go, well, no, because it's 2 lines, not just 1 line. But then I would say, well, the point 1, 1 is in the set, and the point -1, 1 is in the set. But when I add them, that's not in the set. And so therefore it doesn't satisfy rule number 1. Okay. Time for a 30-second break for me to process, have a drink, think of you guys to think of a question. All right. Thank you for bearing with me. So people have asked some really good questions and said some great stuff to help clarify these things. All of those questions are excellent, especially the ones that go, what if, and this is what I'm thinking, is that what it is? Yeah? Yeah, we'll end at 4. Because that's when I have to go home. Okay. So, right. The thing you really, really need to know is if it's written down in one of these formats like this, how do you tell if it's a subspace? And the answer is this. If it's a span, it's a subspace. Span of anything is always a subspace. It makes not the slightest difference what vectors are in here. You could have 20 of them if you like. It makes that they don't have to be independent. They're allowed to be multiples of each other. You're allowed to have the 0 vector. It doesn't matter. Whatever you have here, it is always a subspace. Guaranteed. And what that means is if you can rewrite the thing you have as a span, then it's a subspace. But I will say something. Don't forget that a span is short for, you know, linear combinations. And it has to be all the linear combinations. So if it's not all the linear combinations, then it's not a subspace. Because if it was a subspace, you'd be able to do linear combinations and they'd still be in there. So all of them have to be there. So as a very specific example, this set can be written as T lots of 5, 1, 6 and S lots of 0, 1, 0. So what I did is I went along and I went, well, there's 5 T's here and 1 T here and 6 T's here. And then there's no S's here and there's 1 S here and there's no S's here. That's a span. Because it's linear combinations and I have to use all the numbers. And so that's a subspace. Yay. So if you can write your thing as this, it is guaranteed to be a subspace. If you can't, it still might be, it's just that you can't. But if you can prove that no one can, then it's not a subspace, and that's quite tricky. But you can make a guess. In fact, in general, the time when you can do this trick is if these things are linear functions of the variables involved. If I'd had like an S plus T squared, I wouldn't be able to do this trick of pulling a single T out of every one of them. So if I'd had this, damn it, 5T, S plus T squared, 6T. That would have been trickier. I could have done, you know, damn it, 5t t squared 6t plus 0s0, that's fine. But if I pull a t out of this, there's still a t inside, which is a bit of an issue. So I would say that this is probably not a subspace, but I can't be absolutely certain. It might still be anyway. But if I had to guess, I would say no, it's not. Yep.
So if we presume we have a good question like that, are we allowed to say that we don't have enough information to decide whether it is actually subspace?
I mean, you totally have enough information. You just can't use this rule. If you had 5 minutes left in your exam and you had to make a decision without giving a reason, then I'd say no. That's right. We can tell it's probably not. That's my instinct because of this squared here. Because squares tend to make things curved. And so I would make a guess that something involving that would cause a problem. I'm going to pick t equals 1. 5, 1, 6 is in this set. Because it's s equals 0 and t equals 1. And if I multiply that by 2, I would get this. And that would, if I looked at this, the first coordinate would tell me that 5t would, so if this is in S, if this is in S, then 5t would have to be 10. But, and so the t would have to be 2. And 6t would have to be 12. That works for that one too. And that means that the t squared, oh crap, it is in there. Damn it. Oh, it's Frelling closed under scalar multiplication. That's so annoying. Oh, because the reason it is, because sure, t is 2, that would mean I put a 4 here, but then I could just choose the s to be -2, and that'd be fine. Oh, wow. Oh, I love it. I mean, I hate it too, but, you know, it's a love-hate thing. It must be addition that's the problem. Ah. Okay, I've got it. So what if I had 5, 2, 6? Yeah. That's in S because the little s, the t is 1 and the little s is 1. And then 10, 4, 6. No, it's closed under scalar multiplication. What a world. Yeah, because I can make the s whatever I want. Oh, wow. If I was in the exam doing this, I would probably give up at this point and come back to it later. Oh, are you allowed to come back?
Yeah.
Okay, good. Okay, it's a written exam. Okay, that's good. Oh, some of the other courses have a multiple choice exam and they're only allowed to decide at that spot and they're not allowed to come back. Did you have a question?
No, I have that for my subject.
I'm so angry. I made a very angry tweet about that the other day. Okay, so if you follow me on Twitter, you'll see me complain about a lot of stuff that goes on in maths courses. You will see a lot of just maths, basically, and talking about stuff that happened in the Maths Learning Centre and complaints that, you know, subtweets about exam procedures and my cats.
You cats?
2 cats. Their names are Oliver and Tabitha.
Oh, wait, is Tabitha a tabby cat?
Yes.
Oh.
Okay.
You're the best.
Cellophane. Oh yes, that much. Oh no, the pinned tweet is something I made of cellophane. Yep, we're getting distracted. Okay.
No.
Okay. So I'm going to give up on deciding whether this one is a subspace. I really think it isn't, and it's probably the addition that's the problem. So, yeah, yeah. No, I give up. I'll come back to it another day. I'll probably tweet it. So, I want to tell you though that that's the general rule, and if you do see something that's not a linear function in this spot, then the best bet is to say it's not a subspace. And hopefully the person who's there is kind to you and it has S's in at least 2 of the positions so that it doesn't cause this pain. Okay. Okay, and if it's not all of the linear combinations, then it's not a subspace either. I definitely know this is not. Because this is definitely a linear combination of 2 vectors, but I'm not allowed to use any number I want next to the 0, 5. So it's not a subspace. And I can be sure it's not, because this is a line not through the origin, and that is the worst kind of not subspace. You can't probably say that in your exam, but you can say this is a line, this doesn't contain the origin. So it's not a subspace because it doesn't satisfy rule 0. But I can tell that just because it doesn't have all the linear combinations. But double bluff, that one is a subspace because this one's already a combination of that one.
So you could just get rid of the 6, 7, 5 with the same.
Yep, covers the same things. I mean, if I really want to be pernickety about it, I could say this is a half of 12, 14 here. Or I could say this is 6, 7, and this is 2 T lots of 6, 7. And this is, so this is like 1 plus 2T lots of 6, 7. And if I choose all the values of T, this covers all the possible values in R as well. So this is the same as S lots of 6, 7. If I really wanted to show the working, I just replace this with S. Because if I choose all the T's, then if the T's are negative, I can make negative numbers for what this answer works out to be and be able to make whatever I want. Yay! So this one is a span. That's the big double bluff. As I said, if you can rewrite it as a span, then it's a subspace. All right. So what about the other kind of set? There are 2 other kinds of set. There are sets where you describe how to make the things. And there are sets where you have a rule for deciding if you're in or out. What if it was more like X, Y? That. Or like this. Well, this is R2, sorry. Anything that is in this format that has a rule to satisfy, if that rule is any number of linear equations, and those linear equations are homogeneous, meaning they're equal to 0, then that is definitely a subspace. Guaranteed. If your equation is not linear, it's probably not a subspace. And if your equation isn't even an equation and it's an inequality, like x plus y is greater than 0, it is almost certainly not a subspace. And if your equations aren't homogeneous, meaning they're not equal to 0, it's definitely not a subspace. So it has to be homogeneous, meaning equal to 0, and linear, and they have to actually be equations, not inequalities. If all three of those things happen, guaranteed to be a subspace. If any of them not, then it's most likely not a subspace. So I can look at this and go, not a subspace. That is not a linear equation and it's not homogeneous. And in particular, 0, 0 doesn't satisfy it. But even this not subspace. You know, x minus y is less than 0, for example. If that had been an equals, it would have been a subspace, but that's not even an equation. So that's not a subspace. That's an inequality. And I know it's not because I could actually pick some numbers. I could say minus 1, 0 is in this set because minus 1, minus 0 is less than 0. But minus 1, 0 is not in the set because the x-coordinate is 1 and it's greater than 0. Yay. Okay. So that's pretty much it for those things. Except double bluff. You can tell I'm getting tired, I'm getting louder. I'm like a toddler. This one is a subspace. Because the only way you can add two positive numbers to get 0 is if they're both 0.
So with the subsets before that, with x minus y is less than 0.
Yep.
If it is less than or equal to 0, you said that is a subspace.
No, if it's less than or equal to, still not a subspace.
Still not? Okay.
Because this is still an inequality.
So is it for every inequality ever?
I'm sure there are some that are. Like if this had been a less than or equal to 0, it still would have been because it's still only possible to get 0. So 0, 0 is the only point that satisfies it. And just 0, 0 is definitely subspace. So I wouldn't say that every inequality ever is definitely not a subspace, but it is almost surely not a subspace. Yeah. The reason it isn't is because this is saying that that x is less than y, less than or equal to y. And if I multiply that by -1, then it wouldn't necessarily be true anymore. So if I had x is less than or equal to y, if I had the point 1, 2, that works. But -1, -2 doesn't work. Yeah. And so it's the fact that there's more than one option for how to satisfy this that is the problem. Yeah. And also if I drew this picture, it would be this, and that doesn't go forever in every direction. Guys, for example, this one, if I multiply by -1, I fall out of the set. And I know the pictures that are subspaces, this is not just a single line and it's not the whole plane. And so it's not a subspace. It does not draw the way a subspace draws. And any of those are perfectly legitimate reasons. If you just ask to give a reason, you can say, here is a graph of this set. It's not a line or a plane. Therefore, it's not a subspace. Ta-da. If you're asked to just give a justification, because they did explicitly say in your course, you didn't notice, but in the course notes it is there. It says that they're all lines and planes and 3D spaces. Okay. This took a lot longer than I thought, mainly because of the questions, but the questions are important and that makes it your thing. Okay, so now I'm finally up to basis. Someone's asked, what about imaginary numbers? Yes, but then you'd be in C3 instead of R3. So If you're explicitly told that your vector is in R3, then any complex numbers solutions do not count because you're in R3. But it is possible to say, what about X and Y in C3? Yay! And then your scalars aren't real numbers, they're complex numbers and everything's bigger and scarier. But not that much scarier, just a little bit scarier. Yeah. Okay. Now we are finally up to basis. The point of a basis, now where have we been? Vectors are points. There are arrows if we want to add them or scale and multiply them. If we have an equation that we want them all to satisfy, then that produces a set. And if those equations are linear equations, it'll make a subspace. If we have some vectors and we do all the linear combinations, that's a span, and spans are subspaces. So we know this is true. We know that the span of anything is always a subspace. Here's the thing. If you have a subspace, no matter how you created the subspace, it is always possible to write it as a span. Always. I'm just hearing David Roberts, who's the Maths 1B lecturer, coming in and slapping me because he does a lot of stuff with infinite dimensional spaces, and it's not true there, but we're fine. Every subspace of Rn can be rewritten as a span. So when I said at the beginning, hey, this is span, spans are subspaces, it's not just that spans are a kind of subspace, it's that spans are the only kind of subspace. Every subspace that you could possibly imagine, however crazy you define it, it's possible to redefine it as a span if you want. Okay? And so when you write your subspace is equal to the span of vectors, the vectors in this spot, they are the basis. Only they're not quite, because basis has a very special meaning. I said right near the beginning, when I talked about span, that if I was in 2D, I could span R2 with 3 vectors if I wanted, pardon me, but I only need 2. And so it's, I don't even know if it has a word for it if it's not a basis. I think it's called a spanning set, which seems like circular reasoning. But this thing, it's only a basis if it's the shortest list you can possibly get. So some subspace, most subspaces can be written, actually, other than just the zero vector, any subspace can be written as a span in lots of different ways. And some of those ways have more vectors in this spot than others. But if you can make that the shortest list you can, then it's a basis. And the basis in the sense of I can build all the other things that are in the subspace from those few vectors. They're right in the middle, and I can build the rest by going out from there. And also inwards from there, but that's fine. And the way to tell if it's the shortest is if they're linearly independent. Which I haven't actually defined today. But linearly independent has several meanings and one definition. The meaning is that none of them is already a combination of the other ones. And the reason you would care about that, because if you had a list of vectors and one of them was already a multiple of the other one, well, you don't need it because you can make it out of the first one anyway. And so you can throw that away and it would still be, you haven't really thrown it away, you just don't care. So when I was here and I was choosing 2 points here to make my line, you know, this is the span of 1, 1 and also 2, 2. I can use these two vectors to make this line, but this one's already a multiple of that one, so I could just as easily make the whole line, including the 2, 2, from just that one. I haven't removed 2, 2 from the whole set, I've just removed it from the basis. So remember, the span is turning this into the whole line. If I use those two, I can make the whole line. If I use just this one, I can also make the whole line. So I can remove this from the notation. This one here is the basis. These two here are not a basis because this one's already a combination of that one. So the definition of linearly independent is that one of them isn't a combination of the others. That none of them is a combination of any of the other ones. That's not the definition. That's the description that makes it the most useful idea. The definition is the one that we choose that makes it easiest to do with row operations. Because row operations you can teach a computer to do. So the definition of linearly independent is that if you did some number, I'm going to call A, times the first vector, plus some number times the second vector, plus some number times the last vector, and they all add up to the 0 vector, the only solution, damn it, the only solution is that A1 is 0 and A2 is 0 and AN is 0. That's the definition. That says that if you want to tell if vectors are independent, then you must create this equation, do some working, and have this as the final conclusion, and then you will conclude, yes, they are definitely linearly independent. And you can do that with matrices if you put them as columns and row reduce. And if you get a pivot in every column, then they're independent. That's not the definition either. That's just how to interpret this in terms of matrices. But that's the quickest way to tell if you've got the actual vectors. Put them as columns, do the reduced row echelon form, and there's a pivot in every column. If there's one column that doesn't have a pivot, they're linearly independent. It doesn't matter how many rows of zeros there are, just need a pivot in every column. Rows of zeros are irrelevant to linearly independentness, linear independence. So I'm just going to stop here for a moment. The reason this is so hard is because there's lots of stuff. I've been talking for 2 hours and I haven't even got to everything. And it just takes time to sort through it all and connect it together. So it is very natural and important that you feel like it's confusing. Because anything that's connected in lots of different ways is confusing until you make all the connections. Yeah, just wanted to say that. It's part of my job to make you feel better about the maths too, or at least feel better about the way you feel about the maths. I'm going to let people ask another question about any of that.
You could only do a couple of things to study for the exam. What would be the best things?
If I could study a couple of things for the exam, I don't know what's in the exam. I would definitely know how to find the basis for a subspace, which I haven't said today, but there are lots of examples of it on the Maths Learning Centre website. I would definitely know all the interpretations of what getting to the end of a reduced row echelon form could mean, because there's different interpretations in different contexts. And on the calculus side, I would know all the techniques of integration. I know that was the last thing you did, but from experience of students coming and telling me what's in their exam, there's usually a question that's worth a lot of marks that has a lot of integrals in it. And they'll usually try and package them all together into one question. So we have some number of days, which is approximately 4.
You don't need to remind us.
There's 18 hours of Maths Learning Centre drop-in time left until your exam. So feel free to drop in. I'm going to stop the recording there.